Center of Expertise. We're out of the Southwest Division. This presentation was originally developed by the National Renewable Energy Laboratory. And this is when I was looking for material for this presentation, I found this original presentation, and it looked like a very good presentation that addressed most of the items that I wanted to address in my presentation. So basically, instead of creating a new wheel, I'm just rehashing some old information, an original presentation given by NREL. I have the NREL contact information on one of the last slides in the presentation. So if anybody would like to contact the NREL people, that contact information is there. So what we're going to be covering today is we're going to do a technology overview. We're going to do a commercial and emerging applications discussion, discuss driving factors of waste to energy and variables to consider for waste to energy projects. And we're going to talk about a waste to energy hybrid plant study. So there are primarily two waste to energy paths. The path over on the left is thermal, and that's basically your municipal solid waste, any kind of biofuel type materials. And then the pathway on the right, the biochemical, that's basically your wastewater treatment type systems where you have a digester and you get methane gas. One thing to mention is that the biochemical pathway does not have a strong potential because most of it's already pretty well developed. The wastewater treatment plants, they already have digesters, and that digester gas is being recovered. A lot of that digester gas goes to underfiring the digester, so there's not really a lot of potential in that arena. But on the municipal solid waste and the thermal arena, there's huge potential. It's a massive potential. We're going to get into that a little bit later. One thing to mention, though, that a lot of the biochemical has a lot of biofuels generated, and typically what they'll do after they remove the solids from the digester is they'll take that to a drying field, and so that waste that goes into the drying fields is used for fertilizer, and the farmers buy it. But you could actually use that as a feedstock for a thermal waste to energy plant. So we have three types of processes identified here for the thermal side, and that's what we're primarily going to focus on for this discussion. We have the excess oxygen system, the partial oxygen system, and the no oxygen system. The excess oxygen system is probably something that y'all are familiar with. That's typically incinerator type processes where the municipal solid waste are used in an incinerator, either to just incinerate the municipal solid waste, or to use that waste heat off of the incinerators to power a power plant. So the first line is first column is combustion. That's basically an incinerator, and then we have in the partial oxygen system, that's a gasification system, where our primary goal there is not to produce heat, but to produce gases. So the different gases that we typically generate are carbon monoxide, hydrogen and methane gas. And then the last system, last column under thermal is a no oxygen system, where you have an anaerobic heating process, and you drive off the volatiles, and you get chars and you get gases. It's basically the same types of things as you do with coal to make coke, or wood to make charcoal, but that system has no oxygen involved. So those are the three basic processes that we do with municipal solid waste. One of the things to remember about these processes is that typically there's a residual material of 10 to 25% that still needs to be transported to the landfill. So we still have some landfill requirements with these processes. So this diagram here shows a typical incinerator type device, and what we've identified is that there are 86 existing commercial facilities that combust 26 million tons of municipal solid waste per year in 24 states. The minimal typical feasibility is for units of 300 tons per day or greater. So this diagram is pretty simplistic, but there's actually two combustion chambers. It looks like there's just one combustion chamber, but there's actually two combustion chambers. The first combustion chamber combusts the solids, and that combustion chamber also drives off volatiles off of the municipal solid waste. And the second combustion chamber is where the gases, the volatiles, are combusted. And there's actually two different air streams coming off of the two different air streams that go to the two different combustion chambers. So the first combustion process is an underfed system, and then the second combustion chamber is a overfed system. And then, of course, in this diagram, they show extracting the heat to do power generation with their turbine. And then over on the right, we have a table that identifies the different kinds of pollutants that are produced from a incinerator type plant. And incinerators, the commercial incinerator facilities that produce energy are heavily regulated. So you can see that the average emissions from these incinerator plants is much lower than the EPA standards. So some additional information to add here is that incineration, power generation, is very well developed. 25% of all of the municipal solid waste in Florida are actually converted to energy, to electricity, and 50% of all the municipal solid waste in Connecticut are converted to electricity. So some states convert a large percentage of their municipal solid waste to energy. Other states like Texas and California, they have less than 1%. So, you know, it's not consistent across all states. Some states are heavily into the technology, and other states are not spending a lot of resources in investigating these technologies. But it is a pretty mature technology. As you can see here in this chart, it identifies again the different toxins that come off, the different emissions that come off of the incinerator type plants. So the blue bars there are the EPA standards, and the white bars are the average, and then the green bars are the best-in-class waste-to-energy plant emissions. So you can see that there's a big difference between the emissions produced on an average plant and what's possible in a best-of-class waste-to-energy plant. So in the next diagram, this is just a diagram and some emissions information related to a gasification overview. So up there in the top bar, we can see the different kinds of processes that happen. Over on the right, we have the endothermic gasification reactions. So you can see that the fuels that we generate that can be used for combustion are carbon monoxide, hydrogen, methane gas. So those are the primary gases that we're looking for in a gasification process, where we can use those gases to generate power, or we can use those gases also to power vehicles. So there's lots of different things that we can use those syngases for. And the next slide is a basic diagram of the syngas process. So over here on the left, we can see these are the different feedstocks, biomass, municipal solid waste, and others. So there's lots of different organic materials that we can use as feedstocks for syngas. And then in the gasification process, our syngases are mainly carbon monoxide and hydrogen, and then we can use those gases in a lot of different ways. We can use those gases to generate liquids that can be used as fuels. We can also use those gases directly to power a boiler or an internal combustion engine or a combustion turbine, or we can just extract those gases and use them on their own, either as like a hydrogen to power vehicles or other power plants, or we can mix them to generate alcohols. So there's a lot of different things we can do with the syngases. So we have more flexibility with syngas than we would have with an incinerator. With the incinerator, all you can do is just generate heat and use that heat to power a turbine or something like that, power a building. But with the syngas, we can store that syngas, and we can reduce our solid waste, and store that syngas that we produce, and then use that syngas when we want to, or we can transport that syngas to another location. Okay, so the next slide we've got, it talks about the commercially viable size facilities. They're 300 tons per day or greater, and we have economies of scale that are resultant from high cost of emission control equipment. And then most of these systems use a combustion steam turbine systems, and then our efficiencies are typically 25 to 30% if we just generate electricity. If we do combined heat and power and take advantage of the waste heat off of the steam turbine, then our efficiencies go into the 60 to 70% range. So 1 ton of municipal solid waste can produce about 550 to 650 kilowatt hours. So it takes an awful lot of municipal solid waste to generate power, and that's one of the big drawbacks. You have to have a large storage fields. I think it's we need 130 square feet per ton, and then we're talking about huge amounts, 300 tons. So you're talking about several thousand square feet to operate a plant like this. So it's typically 130 square feet per ton. So if you've got 300 tons per day. That's 30,000 square feet. Okay, so average size of these incinerator waste energy plants is 20 megawatts with an installed cost of $4,000 per kilowatt. Again, the residual ash is 10 to 10% by volume or 20% by weight. The levelized cost of energy is interesting here. That's 6 cents to 20 cents per kilowatt hour. In a lot of cases, your cost of energy is going to be lower than what a resident pays. So that's an indication of why the waste to energy technology is so widespread, is because it's very attractive in terms of other energy sources, and especially in some parts of the country, in Connecticut. Okay, so small scale is 10 to 300 tons per day, and it's typically a synthetic gas type system where they extract the gases and use them for different types of engine technologies or heating technologies. And the install cost for these is $6,000 per kilowatt, so it's a little more expensive in install cost than the commercial scale ones. And then, of course, the levelized cost of energy is also much higher. So that we have economies of scale with the larger systems, but with these smaller systems, you may have more flexibility, but you're going to pay more for them. Okay, and then of course we have emerging waste to energy applications, or half a ton to 3 tons per day, and there's actually some demonstration projects at Fort Irwin and Edwards Air Force Base. There's some important numbers here if y'all can keep up with this. The 3 to 18 pounds of waste generated per person per day, that's typical everywhere. So it's, but that relates to about 1 ton of trash that one person generates per year. That's about how much across the country one person generates. One person will generate about 1 ton of trash per year. So 1 ton of trash can generate from 250 to 600 kilowatt hours. So what that says is that to provide the power for 1 person, you need the trash from 20 people. So if you have, like what we're looking at for the Army, if you have a garrison that you're trying to power using waste to energy technology, then you can't do it with just the garrison. A lot of the garrisons, well, there's a couple garrisons that have got programs going on, but we have a garrison in Texas where it's a Dallas Air Force Base. They've got a project that they're working on right now where they're capturing all the municipal solid waste from Dallas Air Force Base, plus the city of Abilene and the city of Tyre, to power just Dallas Air Force Base. So there's lots of potential, but you've got to remember that one person's waste is not going to generate enough energy just for that one person. You need to provide the power needs of 1 person. You need the waste from 20 people. So even though the cost may be low, you need an awful lot of waste to generate power. Okay, so here's some of the driving factors on DoD installations. The national average solid waste disposal cost is $44 per ton. Life cycle cost for DoD landfills can exceed $150 per ton, and then there's a space limitations. There's 54 active landfills on 38 Army installations, and there's 62 closed landfills that occupy 2,500 acres, and it looks like there may be a potential to mine those existing closed landfills to meet the requirements of wasted energy power generation. Another point that's made here is that using waste energy technologies will contribute to our renewable energy generation and greenhouse gas reduction mandates. So that's an important factor in waste energy technologies. And one of the things to remember on that is that waste energy or municipal solid waste are primarily biofuels, and biofuels are primarily hydrocarbons. So those are renewable fuels that we're taking advantage of. So okay, move on to the next slide. Okay, so we've got we're saying here that the large-scale, commercially proven systems, 300 tons per day or larger, they require partnerships with the local municipalities. So that's what I was talking about previously, is one garrison does not generate enough waste, municipal solid waste, to meet the power demand. So if they want to meet all of the power demands, they have to tap into the municipal solid waste of the surrounding cities. The small-scale systems, they're much more flexible, and they're typically gasification type systems. So the fuels are much more flexible. I mean, the byproducts that are generated are much more flexible. And then also those systems can be used for elimination of hazardous and medical waste. So there's some different applications which make those reduced oxygen or oxygen eliminated processes more attractive. Okay, so the disposal costs for municipal solid waste, they're more attractive for coastal or inland locations due to land constraints and high cost to build new landfills in those areas. And any location where you have a cost of over $70 per ton, then that's a potential for waste energy technology. And then if you have energy costs in excess of 12 cents per kilowatt hour, then waste energy would be favorably considered. Also, there's a particular problem with incineration. If you are required to do incineration, there's, according to the Government Accountability Office, there's 251 burn pits in Afghanistan, 21 in Iraq, and because of those burn pits, the air quality is pretty poor, and so there's some analysis here of some different particulate particulate counts and samples taken in these areas that have a large amount of incineration. So if we can use better technologies and do waste to energy, then we have a much better quality. And this next slide is a hybrid type system that's had some research done on it. So scenario one has solar contributing to the power generation. So you have a flatline power generation, and the waste energy plant modulates to keep the peak output, constant peak output. And then in scenario two, we have a more baseline waste energy plant, and then the solar power generation is allowed to peak during midday. So in this particular study, the levelized cost of the energy produced came to about 11 cents per kilowatt hour. I wanted to go back to this slide. One of the things that's important about this slide is you can see under the gasification bar, the syngas, that our products are CO2 and hydrogen. Well, some of y'all should be familiar with the DOE's plan to convert the infrastructure of the United States to hydrogen. So this is a technology that's actually promoted in that plan to convert the infrastructure of the United States over to hydrogen. So that you can take any kind of hydrocarbons, biofuels, or even oil and gasoline, anything that's got a hydrocarbon in it, you can use this kind of technologies to convert hydrogen. And one of the advantages of that is that you can actually do that in an attainment area, in an air pollution attainment area, and then you can bring the hydrogen into a non-attainment area, and that reduces your air pollution within the cities. And then also you have multiple feedstocks. So instead of just having one feedstock like oil, or natural gas, you can have any feedstock imaginable that has a hydrocarbon in it. You can use that feedstock to generate syngas, and that syngas can be used to power your economy, power your vehicles, power everything. So I've been studying renewable energy for a long time, and one of the things when you look at renewable energies, they typically talk about solar and wind energy. Certain parts of the country have strong potentials for those types of technologies, but the southeast and the eastern United States, those areas of the country don't have very good solar or very good wind, but they do have a very strong potential for biofuels. So even though this presentation is about waste to energy technology, that same technology can be used to capture the energy out of biofuels. And as this map shows, the whole this particular map here is the mean rainfall during the growing season. So and that metric is indicative of areas that have a strong biofuel potential. So you can see on this map that the eastern part of the country has a very strong biofuel potential. So the eastern part of the country doesn't have very good wind turbine or solar wind or solar energy, but they do have a lot of biofuels. So this is not only is this technology, waste to energy technology, used heavily in some states, in Connecticut and in Florida, but the potential is incredible for the whole entire eastern side of the country. And of course, we're working on capturing maybe municipal solid waste to achieve the DOD energy mandates. But there's a lot more potential here than just what you can do with a municipal solid waste. So the next slide, this is the person that originally developed the slide the presentation that we're looking at today. This is Jerry Davis biomass heat and power development and market transformation in rail in Golden, Colorado. So if y'all want to talk to Mr. Davis about the presentation, there's his contact information. And this is my contact information. Dan Berndt, Chair, Waste Energy Center of Expertise out of the Fort Worth District Office. So if y'all want to discuss technology any more with me, or we're kind of lacking resources on the Waste Energy Center of Expertise. We could use people that were going to get involved. So if you're interested in getting involved in the Waste Energy Center of Expertise, and as I tried to point out, there's a tremendous potential in this technology. And if you'd like to get involved, there's plenty of opportunity. Okay, that's all I have for my presentation, Ryan. So if you want to take it over,
yeah. If anyone has any questions at this time, you can write them in the Q&A portal on the left-hand side, or if you've got a microphone hooked up, you can click the raise hand button, and we'll get you. Okay, Dan, it looks like Mark asked a question. If you want to read it and answer that in the chat window.
Would Army Corps of Engineers be willing to do a feasibility study for the, was that Army Reserve National Guard? Yeah, we'd be very interested in getting involved in that. Just, give us, we have been working with a lot of contractors that have been coming in and doing the presentation, the feasibility studies. And primarily what we've been involved in is reviewing feasibility studies done by consultants, contractors. But what we can do is we can get those people, make the introductions so that we can get that ball running. And we've been involved in providing guidance and suggestions to other garrisons that were interested in doing studies. So we've had another question from Ken. It says, Dan, would you be the contact person? And yes, I am the chair of the Waste Energy Regional Center of Expertise. So, and that's one of my responsibilities as a chair is to help the flow of communication and to identify resources and giving this webinar is one of the first parts of the center's responsibilities. We need to present the technology and get the core people and the garrisons to think about the technology and then our responsibility is to promote the technology, developing training, creating contacts, networks for people who can get things done. So. We have another question from Ken. It says, have you been approached by vendors of waste energy technologies? It says, we have been, and would like your input on what we found out? Yes, we have been contacted several times. We get contacted, recently we've been getting contacted about once a week from vendors or from garrisons that got contacted by vendors, and they wanted us to look at their technologies. So, so yes, that is something that has been happening. And we just received another question from Mark. It says, Dan, would you be available for a conference call offline? And again, that answer to that is yes. We do that quite often. So just let me know when you'd like to get a conference call set up. I'll probably try to get my get the regional program manager, the Southwest Division program manager, to sit in on that call. Okay. All right. And last comment there was thanks, Dan. So.